We're back, and we're going to talk about acids and bases now. We're not going to repeat general chemistry because I know you've taken that, you've had that, you've done that. But we are going to talk about a couple of things, and we're still in the set the ground rules of how we're going to approach things kind of mode. So we'll focus more on that. We're also going to do something that you're going to notice a little bit of a what's in it for us kind of thing. What are we doing with this concept? What can we use this concept for? What's this concept doing for us in our biochemistry? So, in general chemistry, you went through all the different definitions of acids and bases. We're not going to do that again. You've done that, and I know you've done that. But what I will tell you is that we are going to use the Lewis definition. You're going to notice a recurring theme through a lot of our stuff where we're donating and accepting electrons. So you'll see it here and you'll see it again several more times. So in general chemistry, you also talked about acids and bases and the acid or base dissociating in water. Depending on how much it dissociates or ionizes, that determines how strong it is. We'll talk about that a little bit more in a minute. Just in the definition point of view, if the acid or the base dissociates or ionizes 100% in water, we call that a strong acid or a strong base. And actually, from here on in, we're just going to talk about acids. Everything we say works for both in terms of what we're going to apply, but it's easier to just focus on one. So we'll focus on acids. If the acid only dissociates a small amount or ionizes a small amount, that's a weak acid. So when you were in general chemistry in the lab and let's say you were using hydrochloric acid for something, they chased you into the fume hood. It dissociates 100%. That's what makes it a strong acid. So you needed to be in the fume hood with it. If you were using something like acetic acid, basically vinegar, no one cared how much you splashed that around because it's a weak acid. Okay, so we're going to talk about dissociation constants. And I'll give you the tools to do a whole derivation, but we're not going to go through it step by step. And if you choose to go through it, you can, but we won't completely go through it. So what we're actually going to do is back up and we're going to talk about equilibrium constants. So we'll come back to this. So what I have is I have a reaction. I'm going to call my acid HA because my H is the hydrogen ion, kind of the business end of the molecule, and it dissociates into hydrogen ion, and we're going to call the rest of it just A for acid. So with that, we can use that. My equilibrium constant is the concentration of the products over the concentration of the reactants. And keeping in mind any reaction is reactants going to products. Also, I'm using square brackets kind of correctly, kind of not. I'll acknowledge that square brackets mean molar concentration. I'm using it as a little bit of a shorthand because we're not using units, so I'm using it generally as a concentration. So I just want to be clear on that in case anyone's wondering why I'm doing the square brackets. So it's the concentration of the products over the concentration of the reactants. So the equilibrium constant is a ratio of how far the reaction has progressed. So if we look at it, let's do two different things. Let's say, let's say case number one, I have lots of product. So what I'm going to have in this K is products over reactants story is I'm going to have K as a big number. So I have lots of product, a high concentration of product, over a small number, low concentration of reactant. So it gives me a big K. So a big K is what I'm going to get if I have lots of product. And the term we'll see is I'm going to favor the products. So favoring the products is a big K and lots of reaction progress. So that's another thing we can say. Lots of reaction progress. Or the other way around, let's say our reaction doesn't go very far. We still have lots of reactant. In that case, when we plug into our K equation here, the concentration of the products is going to be small, a small number. Concentration of the reactants is going to be a big number. So if I divide a small number by a big number, I'm going to get a really small number. So I'm going to have a small K. And I know you could memorize this, but here's the thing with memorization. Give me 30 seconds on my soapbox. You know darn well from experience that when you memorize something, it sticks with you for a short time. You memorize it, get through the test, and forget it. It's a put the fire out response. Here's your problem with that. You have to take boards, and you're not going to take the boards, part one of the boards, for a little over a year. So what you take the time to understand typically will stick with you. What you memorize won't. The more you can have in that understanding category, the less unhappy you'll be the term before boards when you try to get everything back in your head. So I could very well say lots of product is big K, little bit of product is small k, whatever, and you could memorize it. But if you can reason your way through this, it's one less thing to memorize, one less thing to remember. So I'm done with my soapbox. So I get a small k when I have lots of reactant left. I'm going to say things like, I favor the reactant, it favors the reactant, or little reaction progress. So that's the terminology you're going to see. So let's go back to our acid. As you know, most molecules, we're really good at writing them all stuck together, like our acid HA, HCl, whatever, is floating around in water, connected like that. It's not. To whatever degree, our molecules are going to dissociate in water. So our acid, like we said, is going to dissociate into the hydrogen ions. Hydrogen ions are the business end of the molecule and the rest of the molecule. So we can apply an acid dissociation constant. Still the same thing, product over reactant. So my product, concentration of the hydrogen ion, times the concentration of the rest of the molecule, divided by whatever's left of undissociated acid. So that's going to be my acid dissociation constant. Oops, going the wrong way, I'm sorry. Okay, so like we said, the equilibrium constant is telling you which way the reaction's going. If we get a large K, we're going to favor the product. A small K, we're going to favor the reactant. So let's talk about equilibrium. The next thing we will talk about is equilibrium. And here's the thing with equilibrium. Everything is going to equilibrium. We're always going to equilibrium. All right, easy enough when I say that. But here's where you get hung up on that. Some equilibriums are good equilibriums and some equilibriums are bad equilibriums. Even if we're going to a bad equilibrium, we're going, unless we do something to change it. So oftentimes you're going to see us go to a bad equilibrium, change something, then go to a new, better equilibrium. So keep that in mind when we're walking our way through what happens next. So there's a principle that talks about we're always going to equilibrium. The principle is called Le Chatelier's principle. What Le Chatelier said is that we're always going to equilibrium. So if we're in equilibrium and we do something to mess up that equilibrium, we're going to go to a new equilibrium. So a little more eloquent, if a chemical system is in equilibrium and it's disturbed, the system will adjust to restore the equilibrium. So there's a couple of ways of adjusting or messing up at equilibrium. One you'll remember because it's the one we're going to do. We can add or take away product or reactant. We'll talk about that in a minute. The other one is easy to forget because we're not going to do it. If I change the temperature, I can change an equilibrium. Think of you left your coffee sitting around, it got cold, but you remembered that it was not very sweet, so you wanted to throw more sugar in it. So you threw some sugar in your coffee that was kind of lukewarmish, took a big gulp. Then what happened? You felt like you just ate a mouthful of sand. Well, what if I throw it in the microwave? Perfect, I heat it up, dissolve my sugar, change my equilibrium. So that's changing the temperature. The reason you'll forget that with what we're doing is we're not going to change temperature. We're going to assume body temperature. So we'll be constant temperature with everything that we do. We're also going to assume atmospheric pressure. Where we're going with our acid-base discussion is to buffering. So most of the time after today, we're going to assume constant pH too. So let's talk about adding product and reactant though. So I might have A, and in a reversible reaction, A can go to B. So I might have right now A and B in equilibrium. But we said if I do anything to mess up that equilibrium, the system is going to adjust to restore the equilibrium. The way we're going to mess up equilibriums is we're going to add or take away product or reactant. So what will happen is if I'm in equilibrium and all of a sudden I put in more A, so my concentration of A increases, some of that will shift over and increase my concentration of B. So I get a new equilibrium with more of both. Or I'm in equilibrium, I add more B. That'll cause my reaction to reverse and make more A. So some of the B will go over and make more A. So again, I end up with more of both. Or I'm in equilibrium, but I take away some A. If I take away some A, that'll make some B shift over, replace some of the A, and I'll end up with less of both. Or I'm in equilibrium. I take away some B. That will make some A shift over, replace some B, and I have less of both. So if you notice, I'm always going to have either more of both if I add one, or less of both if I add one. The equilibrium will adjust, or the reaction will adjust, go whichever way it needs to, since it's a reversible reaction, to go to a new equilibrium, the new equilibrium being either more of both or less of both. Okay, we're not going to go through this whole derivation, but let's talk about the Henderson-Hasselbalch equation. So everything is here for you to do the derivation if you so choose. But let's go back, just have room to write. So we did our equilibrium constant for our acid. So I have the acid, it dissociates in water into the hydrogen ion and the rest of the molecule. If I apply my equilibrium constant to it, I have the concentration of the products divided by the concentration of the reactant. And if I were doing real concentrations and a real acid in a real equation, I could plug in all those numbers. But let's go back for a second. What we're talking about, or where we're going, is we're going to be buffering. So we're going to buffer, and when we buffer, what we're worrying about is pH. We want our pH most of the time in most of our tissues nice and neutral. So we want our pH, most of our tissues, nice and neutral. Well, what is pH? And I know you've calculated this a million times in general chemistry, so we're not going to do it. But pH is the negative log of the molar hydrogen ion concentration. So pH is a function of the hydrogen ion concentration. So the hydrogen ion concentration, though, is dependent on how much my acid dissociates. The hydrogen ion concentration can be quantified in K. I can rearrange, and if you need any help doing it, if you want to do it, I'm happy to help you. I can rearrange K for the hydrogen ion concentration, plug it in, and show pH as a function of how much dissociation I get. If you want to go through the derivation, everything you need is here, other than a little bit of your logarithmic math. Log of AB is log of A plus log of B, or log of A over B is log A minus log B, in case you don't remember that from college algebra. So plug all that in, and what you're going to get is the Henderson-Hasselbalch equation, showing pH as a function of how much the acid dissociates, how much of the hydrogen ion I'm going to get. Okay, so what are we going to do with all this? What we're going to do with all this is we're going to buffer. So let's talk about buffers for a second and the definition of a buffer. What a buffer does, it's not really the definition, but what it does is it resists changes to pH. If we want our pH nice and neutral, which most of the time we do, there's exceptions, of course, like stomach acid and things like that, we need to be able to resist changes to that pH, because we do reactions, processes, stuff in our cells that, if we don't mitigate it somehow, would cause changes to our pH. So we need some way of mitigating it. So the way we mitigate it is through the use of buffers. So a buffer, a proper definition, is it's the weak acid or the weak base and the salt of the weak acid or the weak base. All right, well, what's that mean? Well, what that means is we're going to use this equilibrium thing. So here's another definition of a buffer, a very, very mechanical one. A buffer is a molecule that will take up extra hydrogen ions, as in pull them out of solution, if I have too many, or give me hydrogen ions if I don't have enough. So let's look at this. Let's say I have a beaker. And I have whatever solution in the beaker, I don't know. And I have some hydrogen ions floating around here. Remember, pH is the negative log of the molar, not attached to anything, hydrogen ion concentration. So pH is based on how many hydrogen ions I have floating around, not attached to anything. So here's a way of thinking about buffers. And a very mechanical way, but it works. Let's say I have too many hydrogen ions floating around, my buffer will go in and the hydrogen ion will become attached to the buffer. Now I don't have as many hydrogen ions floating around, so I lowered this hydrogen ion concentration and raised the pH based on equilibrium, based on Le Chatelier's principle. Or, other way around, let's say I need some hydrogen ions. My hydrogen ion concentration is too low. Now, based on equilibrium, what my buffer can do is give me some hydrogen ions. Cut these loose, put them in solution by themselves. So now I have these hydrogen ions floating around. I increase now the hydrogen ion concentration, lowering the pH. Again, based on equilibrium, based on Le Chatelier. And also, I know it's very simplistic, but it kind of works. It's bringing the Le Chatelier principle, the equilibrium principle in. Just focusing on our free, not attached to anything, hydrogen ions that result from that acid dissociating. Okay, so why do we care about buffering? It sounds nice, we want our pH neutral, whatever, but we kind of need it to be. We're going to do a lot of reactions and processes and stuff. You're going to do a lot of reactions and talk about processes and everything in all of your classes. These reactions and processes are very sensitive to pH. So if we don't have the pH where it needs to be, which most of the time is that of a neutral pH, we can change the products of that reaction. We can end up not making the products we want or making products that we don't want. So that's what makes it so important. So if we want to stay neutral, how are we going to do this? Well, what we're going to do is we're going to buffer. So we're going to minimize the change in pH by having extra acid or having extra base already there. And that's really what our buffer is. So we're going to use the dissociation constant of that weak acid or weak base. And again, we'll just focus on acid. And we'll use that to neutralize, if we're going to focus on acid, tie up the extra hydrogen ions to maintain the pH that we need. Water is a poor buffer. Water is not really an acid, not really a base, because of course it's a hydrogen ion and a hydroxyl ion. So, in equal parts. So we'll talk about water here and there, usually talking about it not being a very good buffer, things like that. So first thing we're going to talk about, we're going to categorize our buffering systems a little bit. And we're going to categorize them on two things. We're going to categorize them on speed. How long do they take to act? And we're going to categorize them based on permanence or lack of permanence. How permanent is the change? So we have different ways of maintaining our pH, of buffering. So we'll talk about that. And we do it in different places. Oops. So first we'll talk about the range that we're trying to stay in. We're trying to stay in a pH range in our blood of 7.35 to 7.45. Sounds kind of narrow, a little dicey trying to stay in that kind of range. But don't forget, pH is a logarithmic function. So even though when we look at it this way, 7.35 to 7.45 sounds really narrow, but remember 10 to the power of and all that with your logarithmic math, it's concentration-wise not quite as narrow as it looks at first glance. So what we're really trying to avoid is we're trying to avoid something called acidosis, which is what we get when our pH goes below 7.45, or alkalosis, something we get if our pH goes over 7.45. So we have these three regulators. We're going to talk about when we get to our actually getting into the mechanics of our buffers, three different systems. And our systems are, we're going to use phosphates. We're going to talk about amino acids as buffers. And we're going to talk about carbonic acid bicarbonate as a buffer. So we'll go through those three individually. They can all fall into all of these systems. So that's why I said with these systems, we're talking about them in two contexts. One is time it takes to take effect. The other is permanence. So first one we're going to talk about is chemical buffering systems. They're quick. They kick in less than a second. The reason they can kick in so quickly is they're very, very equilibrium based. So it doesn't take long to get to equilibrium. So since they're equilibrium based, they kick in really quickly. Since they're equilibrium based, they can change very quickly. So that makes them kind of a temporary tie-up of acids and bases. So this one is going to be your quickest. It's also going to be your least permanent, because I could very quickly go to equilibrium, but I can very quickly go to another equilibrium. So all three of our systems, the carbonic acid, the phosphates, and the proteins, will all fall into that in different contexts. So we'll talk about some of that. Some of that, too, will get left for physiology, because like we said, in a lot of places, we're going to go up to a line, the line between biochem and physiology, again, acknowledging it's a very, very big, wide gray line, but we're going to go up to a point, and then one of your physiology classes will take over. So for now, know your chemical buffering systems are the quickest because they're equilibrium based. They're also the least permanent because they're equilibrium based. Okay, we're going to skip number 2 and go to number 3 for a second. So number 3 is your kidneys. Renal mechanisms. They're the slowest because what happens here is we'll tie up the extra acid or base, and again, we'll focus on acid. We'll tie up the extra acid, we'll get it transported to the kidneys. The kidneys will incorporate it into the urine, and you'll get rid of the urine. So it takes some time to get the extra acid incorporated into the urine. So it's the slowest. And this could be the order of hours, days, whatever. But if I can get that extra acid in the urine, obviously I'm going to get rid of the urine. It's gone. There's no turning back on that. It's going to be the most permanent. I guess I should say most permanent. Then, in between is your lungs, your respiratory mechanism. This one's in between, both in between in time and permanence. So usually the order of minutes to respond takes a little longer than pure equilibrium, a chemical system, but much less time than your kidneys. And it has some permanence, and we'll talk about that with the carbonic acid bicarbonate system. If I can get the extra acid in a form that I can exhale, which is carbon dioxide, and we'll talk about how I'm getting from acid to carbon dioxide in a minute. But if I can get it in there and exhale it, I've exhaled it, it's gone. But it's very equilibrium based in terms of getting it in the form of carbon dioxide. I can very easily go back and get more hydrogen ion. So that's why I'm in between, both in terms of time and permanence. Okay, let's talk about our first buffering system, We're going to talk about phosphate or phosphoric acid as a buffer. So this one's important in the intracellular fluid. It's important in the kidneys, urine, things like that. So I have it drawn here in a very circular form, but we're going to draw it in a more linear form. We tend to think linearly. It just is what it is. So the formula for phosphoric acid is H3PO4. So H3, 3 hydrogen ions, potentially PO4. So we're going to dissociate this molecule, and we're going to think about equilibrium as we do it. So I can take a hydrogen ion off. I can get a hydrogen ion and leave dihydrogen phosphate. But I'm not done. I can take that dihydrogen phosphate. I can take another hydrogen off. Off to the hydrogen phosphate. But I'm not done. I can take that hydrogen phosphate. I can take another hydrogen ion off. And I'm just left with my phosphate. So we could have drawn this in one big line, going from my H3PO4 to H nothing PO4s. So what I have, if I've drawn that one big line from one end to the other, getting from one end to the other, I have 3 hydrogen ions in the middle. So you can look at this, if I drew it as one big continuum, as a sliding scale. If I have too many hydrogen ions, I can use the phosphate to tie them up. Because remember what I'm counting in pH. pH is the negative log of the free floating around, not attached to anything, hydrogen ions. So I can use one phosphate to tie up to 3 hydrogen ions, if that's what my equilibrium needs me to do. Or, other way around, if I need hydrogen ions, and I have this molecule with 3 of them attached, I can start taking them off, moving, this way in my equilibrium, take them off to add more hydrogen ions free floating in my solution to get counted in that count. So it's all equilibrium based. I could either take the phosphate, attach the hydrogen ions, heading in the direction, up here, or if I need them, I could start out with the phosphoric acid and take 3 of them off, heading down in this direction. So like I said, it's a very linear version of exactly the same diagram we had on the previous page, but very, very equilibrium based. I'm just going back and forth, depending on my equilibrium, either getting hydrogen ions if I need them, or taking them out of solution if I don't need them, if I have too many of them. So we're not going to do an awful lot with phosphoric acid and phosphates, but your physiology will. So what you'll be doing in physiology is, for example, you'll be talking about the kidneys, and you'll be talking about phosphates, phosphoric acid, giving you hydrogen ions or tying up hydrogen ions, whichever you need, making the urine either more acidic or more basic to either get rid of extra acid or get rid of extra base. Okay, so you'll talk about the kidneys in physiology, so we won't get into them an awful lot here, at least yet. We might a little bit more next try. Okay, the next one we're going to talk about is carbonic acid bicarbonate buffer system. So we're going to get very, very mechanical with that one also. So this one's the most significant buffering compound in the blood. And again, it's equilibrium driven. So let's talk about this one. We'll, like everything, we'll draw it out. And we're actually going to do some of the things in the end of the PowerPoint while we're doing this, and we'll talk about why when we do it. So carbonic acid is H2CO3. So it can dissociate in two different directions. One is it can dissociate into hydrogen ions and bicarbonate ion. Or, and it can dissociate into carbon dioxide and water. So when we do this, I usually ban two words from your vocabulary when we're discussing it. You can't say right and you can't say left. It's for a couple of reasons. One is we're going to have a conversation that does a lot of right and left and it's very specific. I don't want you to confuse those two concepts. The other one is I just so happen to put the hydrogen ion on the right and the carbon dioxide on the left. I could just as easily have put it the other way around. So I don't want you to start saying, well, if hydrogen goes up, we shift left, shift right, whatever. You're going to stay very specific in your thoughts. If hydrogen goes up, carbon dioxide concentration goes up, or that kind of thing. So I have this equilibrium. So remember our little A to B thing. I had A and B, whatever my reaction was, whatever A was, whatever B was. We said if A goes up, I'm going to shift my equilibrium towards B, B will go up. I'll have more of both. One goes down, I'll shift my equilibrium towards the one that went down, and I'll have less of both. So, same idea here. Get rid of that so we have room. What's going to happen is if my hydrogen ion concentration goes up, I'm going to shift my equilibrium towards carbon dioxide and it will go up. So one side goes up, the other goes up. We're going to focus on hydrogen ion and carbon dioxide because it just works with the conversation. Just for clarity, if hydrogen ion goes up, if hydrogen goes up, bicarb goes down, or if bicarb goes up, hydrogen will go down. So from side to side, one will go up, the other will go up. Within each side, one goes up, the other goes down. That'll get more important in physiology, and we're going to talk about how to very mechanically use this diagram or this equation to get through what you need to get through. So let's go through a couple of things with it. If hydrogen ions go up, my hydrogen ion concentration goes up, that means my pH goes down. Because remember, pH is the negative log of the molar hydrogen ion concentration. When I say that in class, everybody looks at me like, yeah, I know, I've known that since the 10th grade. I know you know it. But what I have seen in questions is once we start, this goes up, that goes down, this goes down, that goes up, it's easy to get on a roll and forget these two go opposite. So that's why I bring that up. So hydrogen ion goes up, pH is going to go down. Also, if hydrogen ion goes up, we're going to shift our equilibrium towards carbon dioxide and it's going to go up. Or if hydrogen ion goes down, we'll shift our equilibrium towards the hydrogen ion, making carbon dioxide go down. So it's exactly the same thing as our A goes to B. One goes up, the other goes up, one goes down, the other goes down. Just don't forget, we've got our inverse function here. Okay, so let's talk about, let's use this, let's do something with it. So what we're actually going to do is we're going to do the last few slides in the PowerPoint. And if you look at those slides, you'll see all these arrows on the bottom. This goes up, that goes down, blah, blah, blah. And again, you have two approaches. You can try memorizing it, and I promise you'll mess it up, or you can reason your way through it. So what we usually do is we do this section in stories. So we're going to tell biochem stories. So let's do our first biochem story. So our first biochem story is I'm going to be a little old man, and I'm 85 years old, and I lit my first cigarette when I was 12 years old. And I'm going to be one of these people that, these really, really bad smokers, really over-the-top smokers light one cigarette off the butt of the other, gross. That's what I did. So I lit one match when I was 12 years old. I've been lighting one cigarette off the butt of the other ever since. So what I've gotten myself is a really good case of emphysema. So very simplistically, very mechanistically, here's what emphysema is. Emphysema is a condition where I've developed so much scar tissue in my lungs that I'm not able to squeeze my lung tissue and force the carbon dioxide out. And I'm being very simplistic because I can right now. Physiology, we'll talk about what that means, what do you actually do to the tissues, the whole story, or I'm just kind of paraphrasing it. So here's what happens. I inhale oxygen, I go through all my steps and processes and things we haven't done yet. I make carbon dioxide, and I really like to exhale it and get rid of it. But because I have emphysema, I can't. So I'm building up, I'm increasing my carbon dioxide concentration. Because I'm increasing my carbon dioxide concentration, that's going to make me shift my equilibrium towards hydrogen ions and increase my hydrogen ion concentration. If I increase my hydrogen ion concentration, I'm going to decrease my pH. So if I decrease my pH, I'm going to become acidic. I'm going to get a condition called acidosis. So there's two ways that I can get acidosis. One is I can get it through a respiratory mechanism. So I can get it through a respiratory mechanism. Or I can get it through a metabolic mechanism. So my respiratory mechanism is going to be something going wrong with my breathing. My metabolic mechanism is going to be something I'm ingesting or excreting that's throwing off my pH balance. So my story was I have emphysema. So it's definitely a breathing issue. So it's going to be a respiratory mechanism. So what do I have? I have respiratory acidosis. So what caused my respiratory acidosis? What caused my respiratory acidosis is I had an increased carbon dioxide concentration that caused an increase in my hydrogen ion concentration that caused a decrease in my pH. I did this through a respiratory mechanism. That's what makes it respiratory acidosis. So that's our first condition, first biochem story. Okay, let's do another one. I'm going to recycle my diagram. I don't know if I put enough blank slides in. Okay, so let's tell another biochem story. Let's say this time I'm hyperventilating. Remember, hypo is not enough, hyper is too much. So if I'm hyperventilating, what am I doing? Well, I'm breathing too much, too fast, whatever. So what I'm really doing is I'm breathing out more carbon dioxide than I should, than I want to or would like to. So what that's going to do is drive my carbon dioxide concentration down. I'm exhaling too much, I'm keeping too little. So what's going to happen? I'm going to shift my equilibrium towards carbon dioxide, drive my hydrogen concentration down. My hydrogen ion concentration goes down. That means my pH goes up. My pH goes up, I become alkaline, or I get alkalosis. How did I get there? Respiratory mechanism or metabolic? Through a respiratory mechanism. So what do I have? I have respiratory alkalosis. How did I get it? My carbon dioxide concentration dropped too low, made my hydrogen ion concentration drop, making my pH go up. All based on equilibrium, all based on Le Chatelier's principle. That's how I got alkalosis, respiratory mechanism, some respiratory alkalosis. Okay, that was our second story. Let's do a third story. Okay, the third story, we're going to stay very simple. Let's say I'm taking some medication. I'm taking, I don't know, what can I take? Oh, here's one. Let's say I was hanging out on my back porch with my little old lady friends. And we heard that if you take an aspirin every day, you're going to have a really healthy little old lady heart. Well, here's the thing. Moderation is not my thing. So, if one gives you a really healthy little old lady heart, one is good, more must be better. So I'm going to take a handful of aspirin, breakfast, lunch, and dinner. So what am I really doing as I'm taking aspirin? What am I really eating? I'm eating salicylic acid. So I'm eating acid. What am I doing? My hydrogen ion concentration, eating acid. I'm driving my hydrogen ion concentration up. Hydrogen ion concentration is going up, pH is going down. What am I doing? I've given myself acidosis. How did I get there? It's not a breathing thing, it's an eating or excreting thing. So metabolic. So what I just described is metabolic acidosis. And we're going to come back to that in a minute. Okay, let's do another one. Last one. What side do I have hydrogen ion on? I want to switch it. Okay, just to do it. Just don't do the left-right thing. Okay, so I have hydrogen ion and carbon dioxide that I'm going to focus on. And it's one way of looking at it. You could focus a couple different ways and get to the same place. So let's say now, there was this infomercial that went around, probably 20 years ago now. So if you were wondering if I'm old, now you know I am. So this infomercial, when they still had those, I guess I dated myself when I said that, was around probably 20 years ago. And what it said was that Tums are a good source of calcium. So let's say I'm still hanging out on my back porch in my rocking chair. I really do have a rocking chair on my back porch. There's too much information, right? So I'm hanging out on the back porch in my rocking chair with my little old lady friends. And we saw that infomercial and we thought, we want really healthy little old lady bones too. So we need to take calcium. We'll take Tums. So again, moderation's not my thing. So I'm going to have a handful of Tums, breakfast, lunch, and dinner. Usually in class, somebody will be smart and say, oh, you're good then. You're balanced. No. So what am I doing? Eating those Tums? I'm eating bicarbonate. So eating bicarbonate, that's going up. So remember we said on one side, one goes up, the other goes down, side to side, both go up, both go down. So my bicarbonate's going up, making my hydrogen ion go down. Hydrogen ion's going down, pH is going up. pH is going up, what am I getting? Alkaline or alkalosis. How did I get there? Respiratory or metabolic? I got there in a metabolic manner. So that's my metabolic alkalosis. My hydrogen ion went down, so my pH went up. Alkalosis, metabolic manner. Okay, so let's back up with this. Here's something. We can have a respiratory compensation for a metabolic problem, but not the other way around, at least directly. When you get into physiology, you'll talk about metabolic compensations, but they're not direct. It's not a one-step. So I can have a respiratory compensation for a metabolic problem. I can't go the other way around. So I can adjust, not consciously, but I can adjust my breathing. I can't eat anything that changes my carbon dioxide concentration. And I know it sounds goofy when I say it that way, but it's the kind of goofy that you remember. So I can have a respiratory compensation for a metabolic problem, such as a metabolic acidosis. So here's what I can do. I adjust, not consciously, but I adjust how much carbon dioxide I exhale. The carbon dioxide that I exhale is a waste product, as in it's the carbon dioxide that I don't need. Let's take that a step further. The carbon dioxide that I exhale, that is that waste product, is a leftover. So think about leftovers. When do I have more leftovers? Let's say I was cooking. That won't happen. I don't cook, I reheat. But let's pretend I was cooking. If I am going to cook, I'm going to cook a lot. Make it worth my while. So let's say last weekend I decided to make lasagna. How am I going to get more leftovers? If I cook a big, huge pan of lasagna or a little bitty one? Big one, of course, right? So because I have a larger quantity to start with, I'm going to have more leftovers. When I have a little quantity, I'm going to have fewer leftovers. So let's go with that. So let's back this story up for a second. What we're going to talk about is compensating for metabolic acidosis. I'm just putting that down there because I want to clear this off and make room. So we're going to continue to focus on hydrogen ion and carbon dioxide. So we'll go back to my little lady eating aspirin story. So I'm in equilibrium right now. This is going to be a story of I'm in equilibrium, I'm out of equilibrium, I'm in a new bad equilibrium, I'm out of equilibrium, and back and forth. So like we said, we're always going to equilibrium, but not all equilibria are good equilibria. So I start out, I'm in equilibrium. Then I eat my bottle of aspirin. When I eat my bottle of aspirin, I drive my hydrogen ion concentration up, drive my pH down, and that's where I get my metabolic acidosis. So my metabolic acidosis is this deviation from equilibrium. But I'm always going to equilibrium. So now what I'm going to do is I'm going to shift some hydrogen ion over and drive my carbon dioxide concentration up. So I have too many hydrogen ions, still have too much carbon dioxide, but I'm in equilibrium now. I'm just not in a good equilibrium. So what do you think of this plan? I'm always making carbon dioxide, doing the reactions and the steps and the processes that we haven't done yet. I'm exhaling my leftovers. How about I exhale some extra? Or my leftovers just happen to be extra. I exhale more carbon dioxide. If I can exhale more carbon dioxide, I can drive my carbon dioxide concentration down. Okay, I'm out of equilibrium again. but that's going to make me go to equilibrium. How? By shifting some hydrogen ions over and bringing my hydrogen ion concentration down. So if I can bring that hydrogen ion concentration down, it's going to bring my pH up. If I can do enough of this, I'm no longer in acidosis. So my respiratory compensation for metabolic acidosis is I want to exhale more carbon dioxide. Just shifting the equilibrium, playing with the equilibrium. Something you've probably noticed in this story that I want to acknowledge now, even though we'll come back to it. We're talking about hydrogen ion and carbon dioxide in the blood, in the lungs. I haven't acknowledged going from aqueous to gaseous forms. We'll come back and talk about that. For now, I want to deal with this in the context of equilibrium because it's a very nice mechanical way of doing it, particularly when you're looking at questions and things like that. So I want you to get this mechanical way down, then come back and we'll talk about gaseous to aqueous and vice versa. So my respiratory compensation for metabolic acidosis is that I'm going to exhale more carbon dioxide. Let's talk about this for a minute. And again, on approach, give me 30 seconds on the soapbox again. What you could do is just memorize that. Simple. Metabolic acidosis, exhale more. Done. But you're going to have so much stuff to remember. Here's the pragmatic reason not to do it that way. You're going to have so much stuff to remember for boards, you don't need more stuff to remember. Here's the real reason. You've got to be able to apply this to patient care. Memorizing doesn't give you the tools to apply anything to patient care. So you've got to be able to apply this, you've got to understand it, you've got to be able to come back to this equilibrium story and reason your way through it to be able to do that. So that's why we're taking the time to do it this way now, and that's why it's so important that you take the time to make sure you can do it, not just remember it. Okay, off the soapbox. So let's do another one. We also have metabolic alkalosis. So let's do exactly the same thing. And I know you can guess where this is going. But I want you to have the concept of this into out of good and bad equilibrium idea. Okay, so the story we told for this one was I was a little old lady eating Tums. So by eating Tums, I drove up my bicarbonate ion concentration, drove down my hydrogen ion concentration, which meant my pH went up, I was alkaline, and that was my alkalosis. So let's back up in the story a little bit. So I was in equilibrium. So I'm in equilibrium, all is well, I'm in equilibrium. Then I eat my Tums. So I eat my Tums, my bicarb goes up, my hydrogen ion goes down, my pH is up, I'm out of equilibrium. We said we're always going to equilibrium. Some equilibriums are good, some are bad, regardless we're going. The way we're going to go to equilibrium now, because my hydrogen ion concentration's down, it's going to make me send some carbon dioxide over to replace it. Remember A and B, A goes to B, B goes to A. I have more of both or less of both. I have less hydrogen ion. That's going to drive my carbon dioxide concentration down. So now I'm in a new equilibrium. Excuse me. But it's a new bad equilibrium. I still don't have enough hydrogen ion, so I'm in equilibrium, but I'm still not good. So here's what I'm going to do. We're always doing stuff, processes that we haven't done yet that make carbon dioxide. I take oxygen in, I do my stuff, whatever that is that we're going to do, and I make carbon dioxide. I exhale my leftovers. But how about instead of exhaling all that carbon dioxide, I keep some of it. So I keep some of it and I drive my carbon dioxide concentration back up. I'm out of equilibrium again. So I've got that extra carbon dioxide, I have that carbon dioxide, and I'm not in equilibrium. But I'm always going to equilibrium whether I like it or not. What's that going to do? That's going to make me send some carbon dioxide over, balance the equation, drive up my hydrogen ion concentration. So I'm going to drive up my hydrogen ion concentration. Now I'm in a new, better equilibrium. So my compensation for metabolic alkalosis is to exhale less carbon dioxide. So I keep some carbon dioxide, exhale less. So again, you could memorize that alkalosis, exhale less, acidosis, exhale more, but two things really easy to mess up, and we'll go to the PowerPoints in a second. Also, very difficult to apply it. Your goal is, well, I know your goal is to get through questions, but your ultimate goal is to be able to apply it to patient care. So anyway, that's our respiratory and metabolic acidosis and alkalosis. We'll come to those slides in a minute. Let's talk about one more buffer. Okay, everything we said, like always, everything I say is in the PowerPoints. Sometimes it's just easier, I think, to draw it. So we do. But everything I do say is in here. Kidneys, we're going to come back to a little bit. Your physiology classes will spend a lot of time on the kidneys. Your job, and just again, setting the ground rules, this is not a difficult class at all. And I know when I say not difficult with respect to biochemistry, some of you don't believe me. But what you'll find is that no one concept is really difficult. And that's really true for most of the program. The hard part, the difficulty is, one of the biggest difficulties is putting the pieces together. That's an academic issue too. I have this piece from this class and this piece from this class, and how do I make it all fit together? So because of that, I try to point out when I can, we're doing this and we're stopping here, but physiology will pick up. So that when you hit the physiology class, I hope you remember, oh yeah, well, we did this in biochem and here's how that fits in. So we'll try to continue doing that, and hopefully it'll help you put the pieces together. And especially, well, not especially, everywhere, but one example will be when you are talking about kidneys in physiology. So you're going to talk about the kidneys excreting either acidic urine or basic urine, the extra acid or the extra base that you're trying to get rid of will go into the urine, you'll excrete it, and that's how you get rid of it. Okay, the last one we need to talk about is proteins. So, works with plasma proteins, hemoglobin, things like that. So let's draw this one too. All right, let's just draw it. See if I left a slide somewhere. Hope I did. All right, good. I don't know if I left more than one, so we might have to recycle it. So here's what an amino acid looks like. And we're going to talk about this, and we're going to do a whole section on amino acids. So I have a carbon. I have an R group. The R group is the variable. It's kind of like an X in math, but in chemistry we say R. We have a hydrogen, we have a carboxylic acid, and we have an amino group. This is the way it's conventionally written. And while we're here, let's talk about a couple of things with amino acids. And we'll do this when we get there. The family of molecules is amino acids. So this is the part that's common to the whole family. Then, depending on what this R group is, might be just a hydrogen, might be a little methyl group, might be a whole branch chain something. Depending on what it is, that's what makes that amino acid that amino acid. So look at it like this. Let's say you have, 5 or 6 brothers or sisters. You're all in the same family. So this part's the same with all of you. You all have the same last name, whatever. But then you're individuals and you're different and you have different characteristics. That's the R group. And that's why you have different names. So that's the way it works with amino acids and families of molecules. Let's talk about something else. We're going to talk about what's called functional groups. A functional group is a name of a particular part of a molecule that describes its structure, kind of so we don't have to describe its structure. So this is a carboxylic acid, and we're going to go through and do all of these, and it'll be really important that you learn them and know them. If you don't know them, we'll be talking about one sometime. You won't know what we're talking about, and you'll lose the rest of the conversation. So this is a carboxylic acid, and this is a kind of funny shorthand way of drawing it. We should be drawing it, we'll leave the rest of our amino acid. We should be doing this. That's the proper way of drawing it. We have a carbon double bonded to one oxygen, single bonded to another, which is bonded to a hydrogen. And the reason we call it a carboxylic acid, the reason we have functional groups, is we get tired of saying, I have a carbon double bonded to an oxygen, single bonded to another one, bonded to a hydrogen. It's just so much easier to say carboxylic acid. Then we shorthand the writing, nothing to do with being a functional group. We just do, chemists just do. We shorthand the writing like that. And I'm spelling that out now because some of you guys, I know chemistry's been a while, and this kind of implies the oxygens are attached to each other. They're not. Then on the other end, we have an amino group. That's that NH2. And again, another functional group. But if we want to draw it properly, the nitrogen's what's actually attached to the carbon, and the 2 hydrogens are attached. And again, this is just our shorthand. We just do that. But if you didn't know better, it looks like the hydrogens are in between the carbon and the nitrogen and actually attaching them, which of course, as you know, they can't. So we'll come back and we'll talk about functional groups. And we're going to spell, even though you typically draw an amino acid, oops, I cut out the R and the H. We typically draw an amino acid like that. We're going to draw it like this now to talk about how it buffers. Let me see if I have another slide. I don't. Okay. We'll erase it. We're going to recycle. Okay, so I've got my amino acid. I'm going to draw it all out, every vivid little detail. Okay, so let's go back to our very mechanical definition of a buffer. A buffer is a molecule that can give me a hydrogen ion if I need it, or tie up a hydrogen ion if I have too many. So let's do, I don't know, which one do you want to do first? Let's say I need a hydrogen ion. So I need hydrogen ions. So that means my pH is too high. I'm too or I could say I'm too alkaline. Here's how I'm going to get them, or where I'm going to get them. Still have my carbon, my R group, my hydrogen ion. I'm going to draw the NH2 the easy way. And what I'm going to do, I'm going to take my hydrogen ion off the end. It's not attached to anything now. It's a free-floating hydrogen ion. I can count it in the molar hydrogen ion concentration that I use to calculate my pH. So I just buffered. I need hydrogen ions. I just got one. Or I can go the other way. I have too many hydrogen ions. Or another way of saying it, my pH is too low. Or I'm too acidic. What can I do? My carbon, my R group, my hydrogen, nothing changed there. I'm going to draw my carboxylic acid the short way now because I'm not going to do anything there. Got my amino group spelled out. I'm going to attach one more hydrogen ion. So now I've attached it. Took it out of solution, took it out of that count that I use when I'm calculating pH as the negative log of the molar hydrogen ion concentration. I just got rid of one of my too many. So very mechanically, very mechanistically, that's how my amino acids act as a buffer. We're not going to do an awful lot with them, but you are. You're going to be applying that in physiology. Kidneys will be one example. Again, talking about how I'm using amino acids to get me hydrogen ions when I need them, get rid of them when I have too many of them. Okay, let's talk about hemoglobin. Hemoglobin is a molecule that we think of most commonly as an oxygen transporter, because it is. Oxygen is not very soluble in the blood, so I need a way of transporting it. I attach my oxygen to my hemoglobin. It goes wherever it needs to go in my blood. I deliver it, and that's how it works. But here's the thing with hemoglobin. It can also bind some other things, reversibly, of course, too. It can bind hydrogen ions, and it can bind carbon dioxide. Oh, interesting. Well, let's talk about something. Remember we had this equation. Oops. I have my carbonic acid. It can dissociate into carbon dioxide and water. It can dissociate into hydrogen ions and bicarb. You can see where this is going. If my hemoglobin comes along and binds some hydrogen ions, what's going to happen? Well, what's going to happen is I took those hydrogen ions out of solution, meaning I lowered my hydrogen ion concentration, meaning I raised my pH. I buffered. Or hemoglobin can come along and give me some hydrogen ions. They were bound to it, it let go of them, now they're in solution. Raised my hydrogen ion concentration, lowered my pH. Or hemoglobin can come along and bind carbon dioxide, lowering my carbon dioxide concentration, making me shift my equilibrium towards it, lowering my hydrogen ion concentration. Or hemoglobin can come along, give me some carbon dioxide, release it, make me shift over, replace the give me carbon dioxide, raising the concentration, make me shift this way, raising my hydrogen ion concentration, and so on. So exactly the same story, exactly the same equilibrium, with hemoglobin being the molecule that gives you or takes out of solution either the hydrogen ion or the carbon dioxide. pretty straightforward when we talk about that. A little bit of a cumbersome slide, but if you think of it just in general as a buffer, tying up or giving you the carbon dioxide or the hydrogen ion, it's doing exactly the same thing as the buffers that we talked about much more generally did. Tough part is when we think of hemoglobin, we don't think of it binding anything but oxygen, maybe carbon dioxide, but we tend to be very focused on it simply as an oxygen transporter. Okay, let's talk about these slides quickly. We actually already did them, but again, just making the point of understanding, not memorizing. So we could have acidosis or alkalosis, depending on whether we have too many or too few hydrogen ions. We can get there two different ways. We can have a respiratory mechanism or a metabolic mechanism. Okay, a few different ways that we can get respiratory acidosis. Basically everything we said, and go through the equation. I would know the equation if I were you, and go through up, down, like we just did. Your alternative is memorizing this stuff, and it's too much work and too high a probability of making an error. We talked about it with very simple, straightforward examples. And we did that because we have to start somewhere. This is trimester 1. You haven't done lung conditions or anything yet, or I have to assume you haven't. I know some of you have discussed a lot of these things in your undergrad, but I have to operate like you haven't. So there's a lot of different ways. I very simplistically picked emphysema and was very simplistic with it. You're going to go back and you're going to spend a lot of time on lung conditions. So all these reasons and ways of getting respiratory acidosis of things you'll come to. I won't expecting questions at this point for you to know any of them, but that's going to be your job when you get here and do all this stuff to relate back to what we did. Respiratory alkalosis, again, we went through very mechanistically, this goes up, this goes down, so you can follow what we did or you can memorize this part. And you'll talk about some of the stuff here and there that we did. We used very simply hyperventilation. You'll get into things a little bit more with that as you go through the curriculum. Next one, metabolic acidosis. Again, memorize or understand. You know which route I would take you, recommend. This one you're going to see a lot spread out over a lot of different places. We have a lot of different ways we can make a lot of different acids in the body. We're going to talk about lactic acid. We'll do that next term. We're going to talk about making ketone bodies. I can make ketones, go into ketosis, and if I go too far into ketosis, I can go into ketoacidosis. One of the most common ways to do that is through diabetes. We're going to spend a lot of time together talking about diabetes. You're going to spend a lot of time through the curriculum talking about diabetes. The reason is the prevalence is going through the roof. So we'll talk about how it can lead to metabolic acidosis. We use the example of aspirin. A lot of medications are very acidic, so you'll talk about that. Metabolic alkalosis, not very common, but it does happen. So you'll talk about it a little bit here and there. Some of the reasons are very, very mechanical. You know, if I have chronic vomiting, I'm going to be losing my stomach acid, things like that. You'll talk about overuse of diuretics, things like that. We use the example of an antacid because it's just an easy example to use. And again, memorize or understand here. Okay, we're going to stop there. We'll do a little bit with buffers here and there through the topics we're going to cover. You're going to do a lot with them as you go through the curriculum. From here on in, and what we're going to do with our stuff, we're going to assume constant pH. We know now how we get to that constant pH. We buffer when we have an influx of acid or production of acid or base. So from here on in, we can assume constant pH. We're going to assume constant temperature. We're going to assume constant pressure from now until the rest of what we're doing. So we'll stop there, and the next topic we're going to do will be enzymes.